Welcome back, everyone. Hope you're doing well. If you have not already, go ahead and be watching the introduction video for Math 632 before you watch this one. This will help you know how to be approaching these sorts of slides and how we are going to be able to succeed in this class. My recommendation, by the way, when you go through these videos, is to have something as far as note-taking to make sure that you have this stuff as you're going through and writing it down. You're saying, okay, this is something I know that I can come back to. Even if it's just like here's a slide reference for this important definition you can see over here in my bottom right, at least for this video, some slide numbers, or maybe you can just do a timestamp on the video if we have some slides where there's not a number for the slide or something like this. This way you have some sort of reference point. And you don't have to just go back clicking through the video the whole time. This also helps make sure that you are kind of keeping your brain tuned in as you're watching this, okay? So let's go ahead and get started here with what we're talking about. We're going to begin this week by talking about vector spaces. Now, the vector spaces that we're familiar with are exactly in this form. They are vectors in Rn. It's got the little X there, so I've got to do this. So vectors in Rn. So before we give abstract definitions, which by the way is going to be the emphasis for us in this class, is to kind of abstractify, go to another level with the definitions that we know of from undergraduate mathematics, perhaps, is that we're going to start, at least today, with giving some of this concrete intuition. We can use the examples that we're familiar with to give us intuition for these abstract definitions. And that's exactly what I recommend doing. Even if I don't put down, here is the example to be thinking of, be thinking about examples on your own, be making connections to things from back when you were taking this course or something similar. Say, for example, in this unit, linear algebra. Well, we'll start with just coordinates in R2. This is how I'll refer to the real number squared, where R is this little bolded font thing denoting the real numbers. So this is the Cartesian product of the real numbers with itself. And pictorially, what we mean by this is just you can take the x-axis and the y-axis. Here's x and here's y. This is a copy of the real numbers down here on the horizontal axis, and this is a copy of the real numbers up here on the y-axis. That's exactly what we mean when we go through and make these claims about R squared, is that we're looking at coordinates in terms of x and y. So that's why we call this the xy coordinate plane. That's exactly what we have going on here. It didn't do it. There we go. Nope, that's not it. I have to do it like that. Perfect. So often these coordinates are written like x1, x2. Right, so this might be a way that we write this in case we don't want to refer to y as its own letter, but instead we want to just number them as this is the first coordinate, second coordinate, x1, x2. But we can also write this coordinate as a row vector, which is just a 1 by n, 1 by 2 in this case, vector, or a column vector, which is an n by 1, in this case n is 2, a 2 by 1 matrix. So these are vectors that capture the essence of coordinates, and whether we use row or column vector depends on the context. We will denote a vector by a bolded letter x, so that's like x equals one of these either row or column vectors, and we'll call each entry in these vectors components, like we might refer to the x1 component or the x2 component, the first or second component. In the case of the xy plane, the x component or the y component instead. Now, note that we can take one of these types of vectors, either the row or the column vector, and get the other by taking what's known as the transpose. The transpose is taking something, instead of making it an m by n, you make it an n by n. What you're doing is you're switching rows of your matrix to make the first row, for example, the first column, the second row, the second column, and so on and so forth. In doing so, you're also making the first column the first row. You're just switching the roles of whatever nth column is doing and making it the nth row instead. So for example, a row vector becomes a column vector because the one row becomes one column. So we say that two vectors are equal if all corresponding elements are equal. So for example, if I'm saying that this thing is equal to this thing over here, what I mean is that in each corresponding component, first, second, so on, that each one is its own equation. In fact, this is exactly how we get systems of equations out of matrices, which we'll talk about later on this week. Now, there's nothing special about having two copies of R here, so we can make a similar definition for Rn. That is, looking at Euclidean n space, or just the real n copies of the real numbers, all in Cartesian products with one another. Now we have column vectors that don't have 2 entries in them, we have n entries in them. So we take the set of all of these vectors, and for now we'll refer to them as column vectors, although that distinction is not too big of a deal for us, with components consisting of real numbers. And that's going to be Euclidean n space. That's what we're looking at here. N because of the number of components inside of this vector. So if I want to write that in set notation, this is kind of how that looks like. You see here I have all n components of my vector, and I'm also specifying here that each component is a real number. You can also see here, I took the fact that column vectors are the transposes of row vectors, and I can also write this in a more kind of linear notation using this sort of format. So one reason for converting coordinates into vectors is that now we can do arithmetic. With coordinates, if you say one coordinate plus another coordinate, it doesn't make too much sense. But you can say take 2 vectors and add them together, because essentially what we have going on here is that each component is specifying its own equation. For example, if I want to take the 2 x and y vectors here and I want to add them component by component, then I say x1 plus y1. That is going to be the x here and the y here. If I add each of those respective components, here and here, then I get the first entry of the x plus y vector, just adding the original ones from before. Then the same thing for the second, the third, the fourth, so on and so forth, all the way to the nth component. And I could do the same thing for taking a difference too, if that's what I would like to do. Taking 2 vectors x and y, and this time subtracting them rather than adding them. So in the way we're connecting those 2 vectors is putting a minus sign in between them rather than a plus. We say, by the way, that Rn is closed under addition and subtraction. What does closed mean? You may know the word closed from other contexts, but here we mean closed under a specific operation. That operation here is plus. So let's say that we wanted to say what closed is in a more abstract sense. If we say that a set S is closed, in fact, let me go ahead and write this on the page. I am good. If we want to say S is closed under the operation, and we'll say that this operation is just something general. We'll call it star. If I want to say that S is closed under star, then what I mean is that for any A and B inside of S, here the upside down capital A is the for all quantifier. So if you want to just say this in English, it reads for all A and B inside of S, then the operation here is something that you can take. Like it makes sense inside of the set that you're working with. You can take A star B, and that's something else that is still inside of your set. So for example, if I take 2 vectors and I add them together, as long as x1 and y1, x2 and y2, so on and so forth, as long as these are all real numbers, you can add them together. You can always add together real numbers, and hence you can always add together 2 vectors because each component is also a real number. So that puts us inside of the set that we had defined on the previous page. So that's what we mean when we say Rn is closed under an operation. We also have another operation that's closed under, and that's the operation of scalar multiplication. That's when you multiply a number by every single entry inside of a vector. So for example, k times x is going to be taking the number k, just some real number, and multiplying it times k in each and every one of the components of your vector. So x1 becomes k times x1. Here, think of k as something like 2. It's just a number here, right? That's just what you're doing, is you're multiplying everything by 2 whenever you do that. So that's what scalar multiplication means. We specify that k is a scalar here, not a vector. We're not trying to multiply 2 vectors and say, okay, just do it crosswise. That's a different type of product. Instead, when we say scalar multiplication, we're instead saying, okay, take the same number and just multiply it through in each and every entry. We say Rn is closed under scalar multiplication because if you take any of these real numbers that you're working with here, whether it be x1, x2, xn, and multiply it times k, you still get something that is in the real numbers. So this is still something that is real. So that's what we mean when we say this operation is closed under addition and scalar multiplication. Now, in general, we are not working with Rn. This is just an example for us. This is just kind of helping us know that we do know what we mean when we say, okay, what does it mean to have a vector space? So that's what we're working with here. We're working with vector spaces. There are many, 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 many more vector spaces than Rn, and we'll give plenty of examples for them. But we do need a more abstract definition to make sure that we know what we're talking about when we say let V capital V, for example, be a vector space? When we say that, we want to be very specific about what we mean. Well, let's think about Rn. What were the things that were important about Rn? Well, one, you have that addition and scalar multiplication are going to be defined. They're going to be things that we can work with, and that these things that we're working with in general are maybe not just real numbers, tiered all together into n-tiered column vectors or something like this. Instead, these are now just mathematical concepts that we're dealing with, that we're saying that you can, for example, add them together or do a scalar multiple times them. So that's exactly why we say here the definition of an abstract vector is a mathematical concept, just as direction and magnitude. That's all I know about it. Is it real? I don't know. Is it something else that is going on? Is it like, I don't know, some other sort of object? I can't say for certain. All I know is that it is a concept that could be embodied by the real numbers, but it does not have to be. A scalar is also a mathematical concept that's characterized by its magnitude and possibly sign. So when we say sign, we mean like plus or minus. That's what we're saying here. In this course, scalars are just going to be the real numbers, at least in general. At some point, we'll talk about things in which we can make the scalar field maybe something else. But for now, we're going to stick with the real numbers. So they're characterized by their magnitude, that is their absolute value, distance away from zero, and their sign. So for example, -3 is characterized by 3 and minus. So that's this magnitude and its sign all put together. So that's why 3, by the way, this is the absolute value of whatever number that is. That's what we mean when we say magnitude here. One second. Bless me. All right. So that's what we say when we have these things going on. Now, we also have a geometric understanding of what vectors can look like. Now, vectors are the things that vector spaces are made out of, but geometrically, we can think about vectors like arrows. They are starting from a specific point and moving on to another point. However, if we move that starting point, it doesn't really change the vector at all. Instead, we're concerned about the arrow's magnitude and direction, and which direction is it trying to go. So, for example, the vector AB might be going from A to B, while the -v can go from B to A instead. This is how we might write a vector in terms of geometric things. Now, what are A and B? They are also concepts, really only given by position. And whatever kind of world that we're living in. And sometimes vector spaces aren't actually giving us points to be working with. So in general, this is more of a geometric understanding of things. When we are actually getting down to brass tacks, we're going to be talking a little bit more about the algebraic way of talking about vectors and things like this. But whenever we use this geometric notion, make sure that we keep in mind that moving a vector in any direction does not change the vector, as long as it keeps its two main key concepts, its magnitude and its direction. Its magnitude and its direction. All right, so let's define a vector space. We are going to take a bunch of things that have vectors combined with them. So let's talk about what these things are. A vector space is going to have the two operations we were talking about before. You can think back to Rn if you want, but addition does not have to look like addition. It does not have to look like it at all. It can look like something else. We're just going to call it addition because it's going to have properties that look to us like addition. And scalar multiplication, there's going to be an operation, all this is formally speaking, is going to be an operation of how the real numbers work with this vector field. I can take the Cartesian product of the real numbers in the vector field, and then there is some vector that gives me that I will call Rx. Same sort of deal, we're going to have some sort of addition that takes two elements in the vector field and says they can interact with each other to give us some other sort of vector. So these are the two interactions that we're going to have happen here. Now, we're going to say that V is closed under addition and scalar multiplication, meaning that these functions that we're defining are indeed well defined from these respective sets, from the sets V cross V to V, as well as from R cross V to V. Now, we want these to also satisfy specific properties, but before we do that, let's make sure we're clear on the notation here. So we're going to start by saying whenever you have something like an element in a set, we're going to use this little notation that's given right here. That's this little logical in symbol. X is inside of a set A. Now, we could flip that if we would want. Basically, the idea is that whatever is the element is on the cusp end of the end symbol and whatever's at the pronged end, like a fork, if you will, the end of the fork, that's going to be the set itself. So whenever an element X is contained within a set A, we will say X is an A, or X is an element of A, and we will write it very much like this. So that's what we have going on here. Then we will also write in function notation this X with an arrow, but with a little stem coming out of the left-hand side of it, kind of like what we have over here. We will say that means X maps to Y. So for example, in this notation here, what's happening is we are sending a point in the domain, that's this, to a point in the range or the codomain, that's X plus Y. So that is telling us what's getting sent and what is it getting sent to. So that's the mapping that's going on. That's what we're trying to define there. Now, what are those axioms? These first four might look familiar to you. These are the axioms that we want addition and scalar multiplication to satisfy. Anything that satisfies these 8 axioms while having addition and scalar multiplication that are closed, that's going to be a vector space by definition. So we're going to say that it needs to satisfy these 8 axioms. Here's A1 right here. For any x, y, and v, it satisfies. What is this one called? I'm a very interactive person whenever I teach, and in terms of videos, it's hard for me to hear you, but maybe you have to shout a little louder. What is this one called? That's right, this is commutativity. So this is commutativity over here. So this is commutativity. So whenever we're working with axiom 1, we're saying that addition is just going to be commutative. This is a way for us to switch two axioms between one another. What is A2 then? A2 is the property of associativity. This is the associative property, meaning that you can add in any order that you want. If you have 3 elements and you want to add 2 and you're like, okay, well, which 2 do I add first? The answer here is that it doesn't matter. If I add the first 2 or the last 2 first, I'm going to get the same quantity either way because both of these quantities are equal. A3 is what? It's the existence of an additive identity, right? So there's going to be a number 0. We'll just call it 0 because it serves kind of like what a 0 vector does in terms of Rn. It serves that same purpose. What does 0 do in Rn? The 0 vector is the thing that if you just put a bunch of zeros in Rn and just start adding those to everything else, well, you're just going to get the same vector back. If you add that to any other vector inside of your vector space, you get the same vector back. That's the general idea behind what the vector 0 is meant to signify. Now we also have A4. What is this one called? It's not additive identity anymore. It's the existence of additive, what is it? It's inverses. Additive inverses just means that whenever you have an x, there is some number negative x. So when you add them together, you get back to the 0 vector. Okay, so those 4 axioms are things that we're kind of familiar with. We have commutativity, associativity, additive identity, and additive inverse for our first 4 axioms here. Now, this is continued to the next 4 axioms, which talk about how scalar multiplication gets to come in here. The first 2 we might be familiar with as well. These also give us something that's kind of familiar to talk about. These are both kind of the same sort of idea of the distributive law or the distributive property. We'll call them distributive laws to signify that you can either distribute in terms of the vectors themselves, that's what x and y here are meant to signify. These are the vectors themselves. Or in terms of the scalars, r and s, you can also distribute that amongst one individual vector. So that's what A5 and A6 are signifying. A5 says distributive law works for vectors. A6, the distributive law works over the scalar field. A7, on the other hand, tells us that we can kind of do the associative property, but this time for multiplication. So this is kind of like multiplicative associativity. Because now we can say, okay, if you have 2 scalars that you're multiplying times a vector s, it's okay to multiply the second vector and then the first vector instead. So you could just kind of do it in this order. And then finally, A8 is that for any x and v, we got the real number 1. If you multiply 1 times the real vector, you get the real vector back. That just helps standardize a lot of our ways of scalar multiplying and specific axioms. Now you might think, John, I do not know how a lot of these axioms actually end up not working. It seems like anything that I can think of addition and multiplication wise, we automatically have commutativity. and distributive law. And we have that 1 times x is x. We have all of this sort of stuff. So what is it that actually makes these axioms worth talking about? And the answer is that there are lots of counterexamples to vector spaces, things that we work with that are counterexamples that do not satisfy one or more of these axioms. And we're going to get to those in just a second. But first, let's maybe broaden our horizons about what actually some of these things can be. First, let's make sure that we know what vector spaces allow us to do. Vector spaces allow us to add a bunch of vectors together thanks to associativity. We can just do it in any order that we want. And this addition is something that is quote unquote well-defined. Let me go ahead and write that here. Well-defined, what that means here is that whenever you think about all the different ways you can get to this quantity, they're all the same. Whether you add the first two first or the last two first and then continue adding, so on and so forth. If we have a vector space, thanks to associativity, I can group them however I would like. I can keep grouping them either like this way, or I can group them like this, right? Or I could just leave the xk by itself and add each one, right? Just in order from left to right or right to left. Whatever that order is, it's always going to be the same. So that is what we mean when we say we can add any number of vectors together and in any order. It's all well defined. We can also subtract vectors. That's a definition for us, by the way. We've only actually talked about addition as our way of going through and defining a function on this vector space. That is our kind of primal operation when it comes to how the vectors interact. But we can also subtract vectors, and we can say x minus y is defined to be x plus the additive inverse, which is guaranteed by the axiom A4. For any y, A4 tells us that we can form the vector negative y. And thanks to that, we can define subtraction of vectors inside of an abstract vector space. Now, we call addition and scalar multiplication linear operation. And what that means is that linear operations are going to be very nice for us moving forward. We're going to talk about them a lot in linear algebra. These are going to be things that are essentially addition and scalar multiplication. So this is very much a definition for us. Pictorially speaking, the idea is that if you have a line going through the origin, something like this, right, then you can always add 2 points on the line and stay in that line. Or you can do a scalar multiple of a point in that line and stay in the line as well. So that's why we call them linear operations. They're operations on a line. If you work on a line, you can always add 2 points in the line, and you can do a scalar multiple of things in a line. So that's why they're called linear operations, and hence the name of linear algebra. We can also form what is called a linear combination of vectors. Let's say, for example, we have a set of vectors, x1 through xk, given right here. Now, each vector individually could be the same, could be different. We just have a bunch of list of things here in this set. Now, don't forget that for unordered sets, the things with the curly brackets here, any repetitions we just automatically throw out. So we can assume each of these vectors is distinct when we write it like this. But for each vector in this collection, we're going to associate to that a scalar. We're going to say for x1, we're going to make it r1, x2, r2, xk, rk. And we're going to have a bunch of scalars with these vectors. Well, we can always take each of these scalars and multiply them times the vectors. That is something that's well defined thanks to scalar multiplication. And then finally, once we get vectors out of each of those, we can add all of those together. That is known as a linear combination. It's a combination of things. Again, you're staying in the line because you have addition and scalar multiplication as your two operations. Scalar multiplication keeps you in the line, and if you add two vectors together, you stay in the line. This is why this is called a linear combination here. So let's go ahead and get to those examples. Rn, we already talked about it. That's kind of our first type of example to be thinking about, which is just the real numbers, just n of them, n copies of it, all in an n-dimensional space. Easy to visualize with n is 2 or 3, harder to visualize later on. But we don't have to stop at n. It's okay for us to keep going to R infinity. R infinity here means the space of sequences. Think of this as like an infinite dimensional coordinate plane. Now, a coordinate hyperspace, if you will, with just a bunch of directions going all which way, infinitely many orthogonal directions. x1, x2, x3, x4, so on and so forth, are all going in each and every way. You may also just want to think about this in a non-geometric sense because maybe you're just familiar with sequences from Calculus 2, and you're just like, okay, this is just a bunch of sequences. This is just a bunch of lines in an ordered list, right? These are, sometimes you can think of these as functions from the natural numbers to the real numbers. That's another way to think of sequences because each natural number is an index here. Our indexing set is the natural numbers. We start with 1, 2, 3, 4, so on and so forth. And when you plug in 1, you get x1. When you plug in 2, you get x2. You get the second element of the sequence. That's what that gives you. R infinity is a vector space. You can add two sequences together. I think I have a slide for this. Let me check and make sure. You can add two sequences together by just same sort of thing as like you would normally do for Rn vectors. You could just add the corresponding components, x1 plus y1, x2 plus y2. And then you could also do a scalar multiple by just throwing in the scalar multiple on each of the vectors. So this does indeed give us a vector space, meaning, by the way, that it not only has to go through and have these operations defined and be closed under these operations, it must satisfy A1 through A8. It must satisfy those axioms from before. Here's a vector space for you, one that is easy to forget about. But the vector 0 is a vector space, just the vector 0 itself. We don't say anything else about it. It's just the vector 0. 0 plus 0 is 0. As long as it's defined to be just the 0 vector, then we're good to go. You can think of this as just like taking the set of all zeros in whatever kind of Rn space that you would like. That's a vector space. But of course, we're thinking more abstractly. This 0 just exists as a concept. This is a trivial vector space that could live in any set as long as it has, say, a vector 0. We also have the space of n by n matrices with real entries. This is going to be a vector space. We can add and subtract matrices. We can do a scalar multiple times a matrix in the same way that we do scalar multiples of vectors. We just go through and multiply each of the entries by the scalar or add corresponding entries of matrices together. This satisfies the axioms A1 through A8. You've got a 0 matrix, which is just a bunch of zeros throughout the entire matrix, and you've got additive identities as well. So you can define each of these things, and then you can show that it goes through each of the other axioms. You also have the space of functions. This one's a weird one to think about. This is actually a vector space. What are the vectors here? The vectors are the functions themselves. Functions themselves serve as vectors. Strange thing, right? This serves as a vector for us. And you have to think, okay, well, how does this fit my abstract definition? What is its magnitude? What is its direction? Well, there's different ways to define magnitude depending on what type of function that we're looking at. So we might want to say, okay, well, maybe it's defined as what it is at 0 or something like this, or something along these sorts of lines. But the general idea is that what is its direction? There's a lot of different directions for it to go into. Like R infinity, basically, you can think that that's R infinity. There's infinitely many directions to go in. That's the same thing for these functions. These are vectors for us. Very weird to be thinking about. But the space of functions, if you define the 0 function and define the additive inverse, that's, of course, going through and taking things like negative f, then you do indeed get the space of vector space of functions. This is called f of r for us, capital F of r. You have a 0 function, you have negatives of functions, and you can go through and show that this has all of the axioms that you would like. You could also limit this to the space of just continuous functions, and this is still going to be a vector space. You can add continuous functions and get a continuous function. You may be familiar from this. Polynomials plus polynomials are polynomials, same sort of deal. So continuous functions plus continuous functions are also continuous, although that proof looks a little bit different. We'll maybe talk about that later on in our calculus section. But C of R is the space of continuous functions. That is a vector space. We can also take C1. This is the space of all continuously differentiable functions. Basically breaking that down, all functions that are differentiable such that their derivatives are themselves continuous. You can prove that this is a vector space. Again, in order for this to work, addition has to be defined, scalar multiplication has to be defined, and it has to keep you inside the set of continuously differentiable functions. Turns out that does it, and it also satisfies all of the other axioms. We could also talk about all smooth functions, infinitely differentiable. You could just take derivatives of derivatives of derivatives. Polynomials, for example, are smooth functions. So all of those things live in there. I've been talking about polynomials a lot. The polynomials themselves with real coefficients, that's a vector space. So all of these are kind of like, you can call all of these, maybe characteristically speaking, you could say that each of these are the functional vector spaces. These are functional vector spaces, meaning that they are all describing functions rather than, points in space. They're describing functions, okay? In fact, you could even include this one. This one is going to be, we'll talk about the linear transformation, which is itself a function from Rn to Rm. So we'll talk about that when we get closer to it. So lots of different examples of vector spaces here to kind of get us started, to let us know that the only vector spaces we're thinking about are not Rn. We're talking about functions sometimes as well. And as we'll see, there's a lot more examples where that came from. But let's get started by proving some things. Again, that's our goal in this course, is to let this be a proof-based course. So what that means is that we want to start by proving things like the zero vector 0 in a vector space V is unique. Let's get out that chart one more time. Here is that chart for what we mean when we have a statement like this. This is what I think is a good idea to build anytime that you're starting to write a proof in this class. What do we have to start with? What do we have to end on? First, we start with the zero vector. And we know what the zero vector is. It has a specific formulation, and that formulation is given right here. This is saying for all x in the vector space, then the zero vector plus x equals x. Notice I've called that zero vector 0, 1 for a purpose I'll talk about in just a second. We also are in a vector space V. That's something that we have right here. Now that vector space V tells us that we have all of the axioms A1 through A8, not just A3, the one for an additive identity. We have every single one of them at our disposal. So it might be nice to make sure that we use some of those axioms here. Now, where we want to end is to say that this zero vector that we're talking about is unique. What does it mean to be unique? In a English perspective, it means there's only one, right? In a math perspective, we'll say there is basically the same thing. There can't be two or more. Let's say that, for example, you had another zero vector. Just call it something else in the world of zero vectors. If you have 0, 1 and 0, 2 both being zero vectors, then in fact, the two zero vectors have to be exactly the same. So you're living in a world where whenever you look at the world of zero vectors and you pick two of them, you realize that you just picked the same thing twice. That is the notion of uniqueness here. So we're formulating it slightly differently. It's the same thing, logically speaking. Instead of saying there can only be one, we're saying there can't be two. If I picked two things, I would have to be holding on to the same object with both of my hands. Is the general idea. So that's what we're going to go through and try and prove uniqueness here. So here we're going to get used to our kind of definition, theorem, proof style of how this sort of course is going to work. Of course, we'll give intuition and things like this. We're not a textbook. We have some ideas of where we are in the class, and we know a general understanding of our audience. And because of this, we're going to be speaking in more colloquial terms sometimes. But whenever we see something like proof, we know that we're trying to speak to something formal. We're not speaking to a specific audience member per se, like you're not speaking to me when you write your homework. You're writing something rigorous. You're writing something based on the axioms of mathematics. And this is what we're going to try and emulate here with this proof. Let's let 0, 1 and 0, 2 be two zero vectors in V. Again, our goal here is to say that if we want to end up with those two vectors being equal, I'm not writing that in my proof yet. My proof doesn't yet say that these two zero vectors are equal because I don't have that yet. That's on this side of the equation. But I do get to start trying to at least formulate this sentence. So I can start by saying if 0, 2 is another zero vector, I just can't conclude that statement yet. So let's see how that works. Let's let 0, 1 and 0, 2 be two zero vectors in V. Now, zero vectors means that they satisfy the zero properties, right? So for example, by A3, since 0, 2 is a zero vector, I can plug in some other vector in for the A3 formula. The A3 formula allows us to say that you can plug in any vector in for X. Well, I can plug in 0, 1. 0, 1 is also a zero vector, so maybe this is strange, but I'm just using the fact that 0, 2 is a zero vector and making this equation. I can plug in any vector for the additive identity. And if I add 0, 2 to an element, since 0, 2 is a zero vector, I should just get the element back. And that's what's going on here. Okay. By A3 again, since 0, 1 is a zero vector, well, 0, 1 equals 0, 2 plus 0, 1. Now I'm using that same property again. The fact that I can always add in a zero vector here. Okay. So 0, 1 equals 0, 1 plus 0, 2 equals 0, 2. That's because I've just found that these two things share a common equality. They're both the same thing. So I could just set everything there equal. 0, 1 is 0, 1 plus 0, 2. And these two things are equal, even though their orders are different by 8, 1, if I'd like to clarify that. So 0, 1 plus 0, 2 is a common equality between 0, 1 and 0, 2, and that should give us what we're looking for. By the way, this will happen sometimes in this class. I'm realizing that I made a slight typo, so let me go ahead and change that here. I'll use a different color. This really should be 0, 2 in order for this to work, right? The reason is that before it said 0, 1, and so I was really setting 0, 1 equal to 0, 1. But the same sort of equation works if I write 0, 2 here. So 0, 2, what that means is that we are adding the 0 vector 0, 1 in for this equation, and that's giving us what we need. So now, since these two vectors are equal, we are done, and we've proven this proposition. Remember that that was our goal at the very beginning, to show that 0, 1 equals 0, 2. That shows uniqueness. So we can similarly show, by the way, using kind of the same sort of techniques, that for any vector x that you choose inside of your vector space, negative x is unique. Let's see if we can maybe just talk through this argument a little bit. Well, let's say that there are two vectors, y1 and y2. And let's say that they both share the negative x property, if you will allow me to call it that. Namely, that whenever I write y1 and y2 and I add them to x, they should both give me 0. And that's because both of these are sharing the negative x property. The negative x property being that x plus negative x equals 0. y1 is the negative x in this case, as is y2. We're assuming that there are two negative x's, and we're going to show that we're holding on to the same thing as we go through and prove that. So that's what we're doing here. So we want to show that basically that y1 and y2 are the same thing. We want to say y1 and y2 are equal. Well, right now we can say that x plus y1 equals x plus y2. Well, why is that? They're both equal to 0. Because of this, we can now go through and write these things like this. y1 equals the vector 0 plus y1. Go ahead and write this in a different color. It's just, this one should be a vector here. So y1 equals 0 plus y1. And then I can write what 0 is. I know that 0 equals y2 plus x. So I could just write in that 0 is equal to y2 plus x right here. And then I'm still adding my plus y1, so I still have that here. And then I can just regroup thanks to A2. I can take those parentheses from the first two terms, move them to the second two terms, get a 0 out of that because that's x plus y1, which also equals 0. And then I'm left with just y2. So at the end of the day, I began with y1 and I showed that it was equal to y2. And that gave me what I need. It's an interesting way of proving it, but we only use the axioms of vector spaces. We didn't just say, oh, you know what? At the end of the day, I'm sure there can only be one, because I've only seen spaces where there's one negative vector for each vector, right? What we did here was we proved it thanks to the axioms that we know of the real numbers. We're not just using an example in our head and saying, oh, there's only one negative number, so let me just explain in words. I'm sure that'll be enough. Instead, what I'm doing is I'm using the axioms of vector spaces to connect things back to the things that we know have to be true for these objects. So we're not just using an example in our head. This is the way that things are, right, in some extent, because of the way that we define them. We know that in a vector space, there's only one 0 vector, and that for any vector, there's only one negative vector associated to that vector. There's another proposition for us to go through and prove some things. We'll call this one the cancellation law. And we'll use a property of equality here that allows us to add and subtract things from either side. And that's something that we're going to be doing here. So basically, the way that we are able to go through and add things to either side is very similar to how we had to do it here. Like here we had x plus y1 equals x plus y2. So we can add and subtract x, for example. And that's what we mean when we say we can add and subtract here. Let's see what that cancellation law means. Let's say that you have this equation. So you have x plus y equals x prime plus y. Well, we're going to say that whenever you add two things by y, then that's going to imply that x equals x prime. That's what we're going to go through and say. All right. So what does that give us? Well, we're going to go through and try and prove this using the things that we have from before. We are given that x plus y is x prime plus y. So if you're making your little flow chart, that stuff goes on the left-hand side. That's on the left-hand side of implies. And then our goal is on the right-hand side. That is x equals x prime. That kind of goes on the right side of our flow chart. I won't draw that every time, but it is a good idea, maybe if you're taking notes or something like that, to try and structure that yourself. I do recommend trying that for a few of these proofs to see if you can understand why the flow of the proof is the way that it is. That helps you understand what the main idea of the proof is as we go through and do it. So let's take these three vectors, x, x prime, and y inside of the vector space such that they satisfy the left-hand side. We automatically get to assume that, that x plus y equals x prime plus y, and that's because we get to assume that in the proposition as well. So we get to begin here. This is where we begin adding negative y to both sides. And then we just have a few different ways of using each of the axioms to help us out here. We're essentially grouping things around. That's by A2. We know y plus negative y is the vector 0. So these should technically be vectors here. And that one is A4. And then once you put those together, you get x equals x prime, like we've done before. Hopefully this becomes a little bit more straightforward the way that we're going through and doing these. We're not taking a step unless there is an axiom that allows us to take that step. This is the general idea. So that is a proposition to prove the cancellation law. There's a couple of other things that we could go through and prove. For example, for any vector x in our vector space, the scalar 0 times x equals the vector 0. Notice the difference in how I formatted zeros here. I was a little bit picky about this earlier on in my typos, so I'll be picky about it here too. 0 is the scalar vector, and the bolded 0 is 0. If I had to write this on my paper for a homework assignment or something like that, I might write it like this. Instead of having the bolded letters, I might put that little hat up on top to say the vector x and the vector 0, very much like this. Well, how do we go through and prove that? We have the cancellation law to help us, so we can start building things up from the fact that, well, you can just take a look at what 0x plus x needs to be. Maybe we can get this to be something that helps us out. So we start from 0x plus x. And we say, okay, well, 0x is, that x is just 1x. That's thanks to A8. So I can go ahead and substitute that in. I can group those together thanks to a distributive law. I believe that one is A6. And 0 plus 1 is 1 in the real numbers, and that's just x. Well, that's 0 plus x because I can always add 0 to any number and get the number back thanks to A3. Now I can use cancellation law because I have two things that are added, the same thing on either side. And so I can basically do the whole subtracting trick that I had from before. So by the cancellation law, 0x equals 0. We can also do negative 1 times x equals negative x. By the way, notice the difference in how the negatives are used here. This negative is given to us in the scalar field. That's a negative 1 times x, negative 1 being in our real numbers there when we're talking. Then you have negative x right here. That means the negative x in the vector space, the one that is defined by A4. We don't define it as just negative 1 times x. We define it as negative x. Turns out this needs a proof. These are all things that you're just like, okay, yeah, sure, absolutely. This is how this works. This needs a proof here. Let's talk about what that proof looks like. By the way, I did try and go through this one without using some of this like mechanisms and stuff. And I was like, certainly this is more obvious than this. And I was like, it does not get more obvious than this. This is exactly how it is done. So I went through and said, okay, well, how do you take these two things and add them together? How would you add x plus negative 1 over x? Is it true that basically we get 0 when we add by this? If we do, then we know that by uniqueness of the negative value of the negative vector, that this has to be negative x, because it's the only one that satisfies this property. It satisfies the property of x plus that vector equals 0. That's exactly how we define negative x. So that's what we're doing here in this line. Okay, so we have x plus negative 1 times x equals, here we go, we have negative 1 times 1x plus negative 1x. That is just using the fact of A8 right here. And then here we're using the fact that we can group those together. This gives us 0x. And normally we wouldn't know what this is, except we just proved that 0x equals 0 all the way up here. So we actually get to say by this theorem, by the fact that 0 times x equals 0, that I can make this equality happen. That was something that was not an axiom, but it was a theorem. And that's exactly why we make theorems in mathematics, is so that we can keep building on the things that we knew from before and getting new things to happen. Okay, so let's see here. That gives us a neat little trick to help us continue to grow our understanding of what vectors are doing. Again, this is any vector space, including the functional ones that we talked about before. But now let's talk about things that are not vector spaces. So far, we've been talking about things that are vector spaces, and it gets us a general idea of how broad the world of vector spaces is. But in order to understand its limits, it's better for us to also get some understanding of things that are not vector spaces. Now, there's a few things we can change. The things that make a vector space are three things. The space itself, so we could talk about Rn, for example. Addition, which you can define to be anything. It's just an association between two vectors, right? Remember that addition is actually just a function that takes the vector space cross itself to the vectors, right? And the same thing about multiplication. Multiplication can just be a way to associate the real numbers cross the vector space into the vector space itself. Like this, for example. This is a way to us to define multiplication. And the question is that if we define scalar multiplication in this way, is what we get a vector space? And this is an interesting question. We've defined multiplication in a very non-standard way. Very non-standard way. This is not the standard scalar multiplication. So when we say the vector space Rn, sometimes you'll see us specify that we mean the vector space with standard addition and scalar multiplication. Of course, if we don't specify that, then we do mean the standard addition and scalar multiplication, but we sometimes might specify this is not the standard one that we're using here. We're using a different formulation for what addition means and what multiplication means. Now, the question is that with this non-standard formulation, is this a vector space? Well, let's go through it. Let's see if we can figure it out. I'm going to take this off. The vector space is closed under the operations. For example, addition works because it's still standard. It's the same as addition as from before. Multiplication doesn't have to figure into that at all. Multiplication is also closed. It's also closed under multiplication. Why is that? Because anytime that I multiply any vector r, or any scalar r and any vector x, I'm always going to get 0. And 0, you better believe, is inside of my vector space. That's the 0 vector inside of Rn. So it is closed. Anytime I multiply two things together, I get something that's inside the real numbers. That's the definition of closed under the operations. So A1 through A4 don't even address scalar multiplication, so they actually automatically still hold. A1 through A4 is fine. Can you think of one through A5 through A8 that may not hold instead? Is there one of the axioms from the remaining 4 that will not make this work? Well, I'll tell you, here are the four axioms again, so that you can be taking a look at those. Is there one of these that doesn't work? I'll tell you that one automatically stands out to me. And that one's going to be A8. A8 stands out to me a little bit because I know that Rn has something else other than the 0 vector. In fact, this is untrue because A8 does not hold. If you take any of those non-zero vectors, you don't get that 1 times x equals the vector itself. You get that that vector is 0 instead. Now, that's not going to work because this needs to be x by our axiom A8. So it actually goes all the way down the list of axioms until the very last one and says, nope, can't make this work because A8 doesn't work. That's why A8 is in there. You may have thought 1 times x equals x. That's clear, right? In this definition of scalar multiplication, it is not. And remember, for our abstract definitions, those things can be non-standard. So that's one counterexample. Working with Rn, but with a non-standard scalar multiplication. What about this one? Let's do another non-standard scalar multiplication, but this time multiplying anything times a vector, it just returns the vector itself. The reason that we might make this change is that, okay, well, we noticed that the issue with the last one was that 1 times x was equal to 0. So what if we would make just anything scalar-wise times x equal to x, like 1? 1 times x is x now, so this has to satisfy A8. Does this break any of our other rules? Is this still a vector space? Well, first we have to check that the operation is closed. Addition, no worries because it's the standard addition is given as right up here. In the scalar multiplication, we start with something that is inside of our vector space, Rn, and we end up with the exact same vector. So by definition, this is going to be closed because we're staying inside of our vector field whenever we take this operation. We just get the vector back itself. What about A1 through A4? Well, those don't address scalar multiplication, so those are fine and good to go. But is it true that we have A5 through A8? Can you think of one of these axioms that doesn't work here? Well, one that stands out to me, and there's a couple that stand out to me. One of them that stands out is A5, A6. I'll just kind of pair those together. And it's because of our distributive property, right? So I'm trying to think about the way that this may work. A5, if I look at it a little bit longer, A5 looks like it might be fine. But I'm curious about A6. What happens with A6 if I go through and try and do this? Let's try and work A6. How would I go through and start exploring A6? Well, maybe I start with taking just any vector. And I say, okay, what is this operation going to give me when I take a look at r plus x times the vector x? Well, I know that for anything that I plug in for a scalar, if I multiply that times the vector, I'm just going to get the vector back. So this is actually just x. So our left-hand side of this axiom is just x. What is my right-hand side? Our right-hand side here is going to be r times x, which we know by definition is x, plus s times x, s being some other sort of scalar. Well, we know any scalar with this product, when you multiply it times a vector, just returns the vector itself. So that is also x. And we're adding those two things together. So A6 is saying that x is equal to x plus x. Is this true? Only in one case is it true. And that's only true when the vector x is, I can subtract from both sides, remember, that's allowed when this is the zero vector. I have news for you. We are not in the trivial vector space. If we were in the trivial vector space, this would be fine. But we are not in the trivial vector space. We are in Rn. So we can say, actually, that this is going to be untrue because of A6. If we have any non-zero vector, then we can get that the vector is, say, for example, 0 plus 1, dot product with x, and that's going to give us x plus x when we go through and multiply everything there. So indeed, the vector x is 0, and this contradicts what we had before. You may be familiar with this terminology. I'll go ahead and repeat it. When you have a contradiction, and unfortunately I've covered it up a little bit with this little dot thing here. Maybe let me do this. Here we go. So now the dot is gone. Whenever you have these two vectors going on here, like these two statements, x is not equal to 0 and x equals 0, what's happening here is that you have a contradiction at play. You proposed something that, and worked with it with that contradiction if x is not equal to 0, and then you ended up that x was equal to 0 anyway. It ends up being a contradiction. And that only works, though, if you can find something that actually makes this contradiction work. Namely, can you find a vector x such that x is not equal to 0? We can, because we're in the vector space Rn. So this is the essence of a contradiction proof. You assume something and derive something absurd. We assume that x is not equal to 0 in order to continue, and then we got that x equals 0, which is absurd because that is contrary to what we had assumed. Okay, so that is the essence of a contradiction proof that I also wanted to kind of just touch on before we moved on. Now let's think about some of these things, and I want to encourage you to think about this one as well. Let's think about this example. This one has a non-standard addition and a non-standard multiplication. We're still working in R, but this time it's just the positive numbers for our vector space. By the way, you can go through and see with this addition and multiplication, you can ask the question, is this really closed under this addition and multiplication? Now, we're not asking under the standard addition and multiplication because positive numbers aren't closed under the standard addition, right? We know we can subtract numbers, and 1 minus 2 is not a positive number. So it's not closed under the standard addition, but we're not using that here. Instead, what we're using is a non-standard addition. X plus y is, what is this? xy. That is actually the product of two numbers inside of the real numbers. Okay, and then take a look at what our product is. It is not r times x, it's actually x to the r power. Okay, this looks interesting. So basically what we're saying is that you're taking addition and making it multiplication, and multiplication and you're turning it into exponentiation. If we stick in just the positive numbers, the positive real numbers, is this a vector space? We need to go through and check each of our bits. Now, again, there's a checklist here. Let's make sure that we're familiar with what that checklist is. We need to make sure that this is closed under addition. And again, this is the addition that we're working with. This is this little circle plus, if you will. there. While we're checking addition, you may also decide, okay, I want to go ahead and check A1 through A4, because those are the ones that have to deal with addition, just addition on its own. Then you get to ask, is this one closed under our scalar multiplication? And that one is, in this case, just the little circle dot. And so then you can ask, does this one satisfy the rest of the axioms, A5 through A8? That checklist has to be completed in order for us to determine if this is a vector space. Remember, if one box is not checked, it's not a vector space. Everything has to be checked. I recommend that you go through and look at this one a little bit. Of course, we're going to go through and do this ourselves, but I recommend that you go through and look at this a little bit and convince yourself one way or the other. Come in with a bias. Come in with a bias that says, I think this works or I think this doesn't work. So before we go on to the next slide, see if you can get a bias from one side to the other. Let's go ahead and move on. First, the positive real numbers are closed under multiplication. You can take two positive numbers and still get a positive number. If x is positive, then actually x to the r power for any real number that you pick, remember for r, you get to pick any real number, including negative numbers, but that's only for our exponent in this case, not for x. So we can actually go through and say even x to the negative 1, which is just 1 over x, still positive because x is positive. So this space is still closed under the plus and multiplies that we've been defining here. So we've got something that is closed underneath the operations. Now, let's think about whether it goes through and satisfies the axioms. So throughout, let's let x, y, and z, the vectors, be x, y, and z in the real positive real numbers, respectively. And then let's let r be the scalar number that kind of will serve as our exponent throughout all of this. In A1, is it true that x plus y is y plus x? Be careful here. We're not talking about plus. We're talking about product, right? We're talking about this little circle plus, which means that whenever I write xo plus y, something like this right here, I'm actually referring to xy because that's the operation that I'm working under. Is this true? Yes, it is, because xy is yx. So this does end up working. So that's A1. A2 says, can I multiply associatively? I sure can. Nothing wrong with associativity in the real numbers. So that does work for me. A3 says, can I find a zero vector? Here is our really first stumbling block. Can I find a zero vector for this vector space? The thing that helps us out, first of all, notice that whatever it is, it can't be zero because zero is not positive. So it's not even in our vector space to begin with. Our zero vector needs to be something inside of our vector space. But note that the zero vector does not have to be zero in our vector space. This one's a big one. Note that the zero vector does not have to be the number 0 or anything really associated to 0. It is just a vector with the property given above. Whenever I operate it in terms of my addition property on either side, I get the vector back. Can you think of something for which that works when I'm thinking about multiplication as my circle plus symbol? That's right, it is the number 1. 1 ends up being my zero vector here. So make the zero vector equal to the number 1 inside of my vector space. Then, whichever way that I circle plus things inside of this vector space, I'm going to get 1x, and 1x is equal to x. So that gives us what we want. The zero vector is 1, kind of a crazy proposition, but it doesn't stop there. What about negative numbers? Negative numbers are not in our vector space. What do you think is going to be the corresponding idea of a negative number? Remember, our circle plus is really multiplication inside of the positive real. So what does it mean to say negative of a vector? You may have gotten this one right. This is 1 over x. Take the negative vector, that means the one that's specified in the axiom property, to be 1 over the number x that is signified by the vector x. Then taking the O plus of these two vectors gives us 1, which, by the way, 1 is our zero vector, so that does end up getting us to that axiom. A neat little interplay between A3 and A4 there. Make sure that some of this stuff is not lost on you, namely the fact that we actually wanted this to be equal to 1 because that's our zero vector. That exactly is what we want to cover in terms of A4. Then we can keep going with A5, A6, A7, A8. This is going to work. A lot of these first ones are going to work thanks to the exponent rules. You can check through these on your own if you would like. If you go through and check A5 through A7, all of these are just the various exponent rules for different ways to write exponents in terms of this. Now, the thing is that, again, we're not talking about multiplication here. We're not saying that all of this is true for any scalar inside of the vector field that we're working with and then just multiplying times r. Instead, we are thinking of r as the exponent. That's the important thing here. And then finally, A8, 1 times x equals x. It sure does, because x to the 1 power equals x. Every axiom works. This is a vector space. So we can conclude from all of this that V, O plus as we defined it, and O dot as we defined it, is a vector space. This is a vector space. VS here is to abbreviate vector space. We have checked all of our boxes. A weird vector space, but we've gotten another example now. What about this one? Let P sub n be the set of real polynomials in the variable x of degree less than or equal to n. The question is P sub n a vector space? Here we're doing everything under standard addition and multiplication of functions. If we ever don't specify that, then we mean that that's what's going on. It's the standard addition and multiplication. Try working through this one yourself a little bit. I've given some ideas here. Remember that polynomials are of the form P of x equals, you've got all these terms and powers of x and stuff like this. To add polynomials, you're adding coefficients of corresponding terms. To scalar multiply a polynomial, you're multiplying each term by the scalar. The hint here is that, yes, this is a vector space. And I go through and tell you what the zero vector should be and also what the negative vector should be for each polynomial. So check this out on your own and see if you're able to make some headway on what this sort of stuff could be. But that does cover it for us. That gets us an introduction into abstract vector spaces. Again, the big things that we learned here is that there are axioms to vector spaces, the things that we're looking for. Defining them is a very rigorous process, and showing examples of them takes some time. In fact, showing something as a counterexample can also take some time because we have to go through our axioms a little bit. But we have learned a lot of different examples of vector spaces here in this video that are worth reviewing. Thank you so much. Have a wonderful day.